closing. Today is my great pleasure to have Professor Jorge Piekarewicz. So Jorge received his PhD in theoretical nuclear physics from the University of Pennsylvania in 1985 and carried out postdoctoral research at California Institute of Technology and the Indiana University. So in 1990, he joined Florida State University, where he has been there ever since. And Jorge main's research interest focus on the behavior of nuclear matter under extreme conditions of density, such as those found in the core of neutron stars. So thank you very much for visiting us.
Thank you very much for the wonderful introduction, and thank you all for coming. And I'm sorry about the dead animal in the other room. I think we're gonna do fine. Let me see. Oh, I know what I need to do. One more second. Let's see if this works. That's okay. I can go like this. Okay. So, so I have many friends in here, and I was reminding myself when was the last time that I visited WashU, and actually I found the slides. It was 2008. Then at that time, the nuclear theory group had Mark and Jim. Since then, it has expanded by a factor of 2, and I'm sure that you're delighted to have these wonderful, talented ladies join you. The other thing that was very interesting is that even though I was trying to talk about the many phases and phases of neutron stars, I never showed the mass-radius relation, which is probably in my field the most important diagram. And the reason is that there was no practical information at the time. So we didn't have any very massive neutron star that constrained the equation of states at the highest densities. So basically the maximum mass that we had at the time is about 1.4 solar mass, what they call the vanilla type neutron star. But since then, I mean, of course, we have been able to gather an enormous amount of information, and particularly on very massive neutron stars. And by that, I mean masses of the order of 2 solar masses. And these 2 solar mass neutron stars place an immense amount of constraints on the equation of state, and I'm going to talk a lot about them. So let me take you a little bit through the anatomy of a neutron star, and the way that I like to phrase the question is, how does matter organize itself? So imagine that you are at densities which are comparable or even a little bit larger or a little bit lower than what you see in atomic nuclei, and then you ask yourself, what is the ground state of that system? So basically you put baryons, or you put nucleons, protons, neutrons, you put electrons, leptons, so that the whole system is charge neutral, and then you let them equilibrate. And if you need beta decays to set the average between neutrons and protons, you do that, and then you just wait and say, what is the ground state of the system? So what do we know about that? So then let me start actually from the core of the star. So here in the core of the star, you see that in this wonderful picture, we have a question mark. And a question mark means that at the densities that we expect to have in the core of a neutron star, which are, let's say, 5 to 6 times more dense than what you see in atomic nuclei, we really don't know very much about what are the constituents of matter. Your chair used to work, and I think he still does, on this area. For example, a very exotic, interesting state of matter is a color superconductor. The question is, can that state of matter be realized at the densities that you can achieve in a neutron star? And the answer is probably not, but the jury is still out. So basically what I'm trying to do now is I'm going to go from this question mark to the next layer, which we call the outer core. So the outer core essentially contains most of the size of the neutron star, about 10 kilometers. And then we believe that it's made of a uniform system. So imagine that wherever you sit in that system, you see the same thing. And it's made of normal constituents. You have neutrons, you have protons, and then you have leptons, both to set chemical equilibrium and charge neutrality. And one of the things that my high energy colleagues always get impressed is that I tell them that basically if you want to enforce a chemical equilibrium, the number of muons in a neutron star is typically 10 to the 56. And that's a very, very large number of muons. So this is the uniform phase. And then as you move out towards the cross becomes non-uniform. So what you have to remember is that the short interaction is short range. So if the system becomes very dilute, namely if the density becomes very, very low, it's energetically favorable for uniformity to break, and then you make clusters of protons and neutrons, which we call, of course, nuclei. So the idea is that basically what's going to happen is that as you go farther outside into the outside of the star, then you're going to make essentially a system which will be non-uniform, but in the language of condensed matter physics, they have what's called Coulomb frustration. And what that means is that you may have a preponderance of quasi-ground states, many, many states with almost the same energy, but completely different topologies. And that is what we call in the community by the name of nuclear pasta. Because they do look, when you do the simulations, like little spaghettis or lasagnas or gnocchi or whatever your favorite pasta is. You have to tell me which one. And then as you go further out, then basically all the neutrons and the protons are contained in nuclei. And those nuclei, because the system is now at least as far as the range of the nuclear force, it's very dilute, then you make nuclei, and then those nuclei decide that the best configuration, energetically wise, to arrange the semis in a Coulomb crystal. So again, in the language of condensed matter physics, it is called a Wigner crystal. But the crystal is not made out of electrons, but it's made out of exotic neutron-rich nuclei. And basically, even though I haven't said much about the electrons, it is the electrons that drives precisely this movement of this Coulomb crystal from low densities, which is essentially the nucleus, iron 56, which has the lowest mass per nucleon, mass per particle, all the way to what we predict is going to be the ground state of the system at the densities, at the bottom densities that you can find in the outer crust. And this is a nucleon that is called krypton-118. Krypton has 36 protons, and it has 82 neutrons. 82 neutrons is a magic number for nucleids, where you get a lot of stability. And the prediction is that krypton-118 is going to be formed. And I talked to Lee this morning, he's going to make the measurement of krypton-118. Hopefully. Again,
Next slide.
So
I have to go there.
So basically, so these parts are also very important, but the nuclear physics is not very dramatic in here. So I just want to concentrate on here, and then just remind you that that's basically what we're trying to understand. If you have a cube made of baryons and charged neutral leptons, what is the ground state of the system? And as you can see, it's a very, very exotic state that you can in principle form.
Perfect.
Yes.
You might add to this that it's most likely superfluid and superconducting as well. I mean, it may not be really relevant for what you're interested in, but it is another exotic form of,
absolutely,
of physics associated with a neutron star.
Yeah. So I'm not going to say more because we've already said it. Thank you. But yeah, I mean, so some of the neutrons which are part of this Coulomb frustrated part might be actually superfluid. Some of the protons might also actually be superconducting. So it's extraordinarily rich, and of course that's why we like it so much. Right?
The muons that you said, they are mu plus and mu minus, right?
Excuse me?
The muons.
The muons are mu minus, because essentially what you have to do is, so you think about neutron, protons, and electrons, right? So the electrons are there just to establish charge neutrality.
Okay.
But when the Fermi surface is very large, it's energetically favorable, instead of packing more electrons, just to put some muons. So it's mu minus. Is that okay?
Yes.
Okay, so then let me tell you about the equation of state, and which is essentially the basic input that nuclear physics brings it into the game. So again, you might all know that neutron stars are the remnants of very massive stellar explosions, we call core collapse supernova. And then if you want to understand the structure, namely, for example, the mass versus radius, then you have to solve what's called the TOV equations, which is nothing more than Newtonian gravity, but with corrections from general relativity. And you can see, you can have them here. So in blue, this is the equations of hydrostatic equilibrium that you use, for example, if you want to solve for a white dwarf star. But then for a neutron star, which is much more compact, you need relativistic corrections, and the relativistic corrections are here. But then you see something very, very interesting. So then you have essentially the equation for the mass enclosed by the star, and then the pressure gradient, right? And you can see that the pressure gradient is always negative, because that's what hydrostatic equilibrium is. At every stage, if the pressure gradient that is fighting against gravity, the pressure is largest at the center of the star and then goes down as you go towards the surface. But there is an interesting connection in here. You have the mass, you have the pressure, you have initial conditions, but there is a quantity here that is lurking that you have no information whatsoever. So if you do not connect, for example, the pressure to the energy density, then you cannot solve the equations. So then what we have is, in the case of any star in equilibrium, you need to provide an equation of state, namely a relation in this case, that it's going to tell you what is the pressure support as a function of the energy density. Without this equation, which we call the equation of state, you cannot solve the mass radius relation. So basically, in 1939, when general relativity was already in the market, the T is for Tolman, the O is for Oppenheimer, the D is for Volkov. They solved the equations, but they assumed that the pressure versus energy density is that of a free Fermi gas of neutrons. So if you have a free Fermi gas of neutrons at 0 temperature, because they're fermions, you cannot put them all in the ground state, you have to pack them. And then the neutrons that are moving the neutrons at the top of the Fermi surface, they're moving very fast, they're colliding, and they're providing pressure support. And when they did that calculation, they obtained this number over here. They said the maximum mass that can be supported by the Tolman-Oppenheimer equation is of 0.7 solar mass. So if you take these equations, you put a very simple equation of state, namely that of a free Fermi gas, then you predict that neutron stars with a mass in excess of 0.7 should not exist. But of course, back already in 2010, we have these very massive neutron stars, and of course, all others as well. So the idea is what provides the pressure support in order for the star to be able to make it all the way to 2 solar masses. And that is nuclear physics. So nuclear physics has a particular characteristic that the interaction at very short distances is highly repulsive. So if the interaction is highly repulsive, when the density increases, then that extra pressure support can support the star all the way from here to 2 solar masses. So I like to say that the increase from 0.7 to 2 solar masses transfers ownership of this problem to nuclear physics. So what nuclear physics, part of what we do, is try to actually have educated guesses for what is the pressure as a function of the energy density, or namely the equation of state. And you can see also that before the GW170817, which is the neutron star binary that gave us the first direct information about gravitational waves from this system, then we only have this star over here. And if you want to say what is the radius associated with one of these sources, the error was of the order of at least 6-7 kilometers. And you're talking about an object which has a radius about 12 kilometers. So the error depending on the model, the error in the radius or the uncertainty in the radius was just enormous. So at this point, all that we knew, basically before GW170817, is that your equation of state has to be stiff enough, or namely push hard enough, so that you can put support to solar mass neutron stars. That was basically the only constraint. In 2005, actually with a student, we calculated an equation of state by only including information about finite nuclei. And because there was no constraint whatsoever, we essentially said, okay, the maximum mass that you can support was of the order of 1.7, because we didn't have any information to constrain the equation of state at the highest density. And then GW170817 came along, and then that's the story. How much does astrophysics is now constraining the equation of state? So let me just tell you very briefly a few concepts that you probably already know about the equation of state. When you were in grade school, you knew about the simplest equation of state, now namely that of a non-interacting classical gas. Low density, very high temperature. The pressure as a function of density and temperature is just the ideal gas law. Then when you come and take your first class in thermal and statistical mechanics, you find out that there is a completely different system in the opposite regime. Now the temperature is very small and the density is very large. So now you have a non-interacting quantum gas. And then the pressure as a function of the density goes like 10 to the 4/3 if you are a ultra-relativistic gas. And this is basically because you're trying to pack fermions at 0 temperature, and you can only put 2 of them for spin 1/2 particles. The next has to go to the next level, the next level, the next level. By the time that you finish, if the density is high, these particles are moving very, very fast, and they're providing a very useful source of pressure support. So this is purely quantum mechanical pressure support. So let me tell you what happens in the case of nuclear physics. One of the things that as nuclear physicists we're very proud is that we have 2 species that we can play with. So we have neutrons and we have protons. So if you have a symmetric system with equal number of neutrons and protons, I call this my symmetric bucket. Imagine again, you're at 0 temperature, and then you just have to fill them until you don't have any more particles. And then as the density increases, you calculate essentially an equation of state that looks like this. So the energy per particle as a function of density takes this form. And one of the main quantities in nuclear physics, or my main concepts, is the concept of saturation, which means that the pressure at this density is like a sweet spot in the how close do the nucleon should get. And at this density, essentially the pressure equals 0 and the system is bound. But much more interesting in the case of neutron stars is what happens when you make the system neutron-rich. So when you make the system neutron-rich, you're taking some of the protons and then you make them into neutrons. But of course, neutrons already have many of the levels occupied, so they have to go again and again to the higher states. And this is going to penalize the system, it's going to impose an energy price. And the energy price is called the symmetry energy. So that's a concept in nuclear physics, which is very important, which basically it's telling you what is the price that I have to pay in making a system with the same number of particles or at the same density that consists exclusively out of protons. So this is the energy of pure neutron matter. And then I compare it with the same system, but now for symmetric nuclear matter. And this is called the symmetry energy, and that saturation density has a value that we call J. But most importantly is what is the derivative of the symmetry energy. And the derivative of the symmetry energy, we also give it a name. We call it L, but you can always think about L as what is the pressure of a gas made exclusively out of neutrons at this magic density that we call saturation density. So we say that the equation of state is very stiff. Namely, the pressure is very effective in the case of neutron stars against preventing gravitational collapse if L is large, or the pressure of pure neutron matter is large, and it's soft if it's small. So that's essentially equation of state 101. Okay, so then what happens? In 2015, we saw the first evidence of direct detection of gravitational waves from the binary collision of 2 black holes. And 2 years later, we saw the first evidence of multi-messenger astronomy, in the sense that you had 2 stars, 2 neutron stars. The neutron stars, I'm going to play a little movie. The neutron stars are going to revolve around each other. As they get closer and closer, they're going to start emitting gravitational waves. And as they get closer and closer, one of the stars are going to deform each other. they're going to create mass quadrupoles, and those mass quadrupoles become a very efficient source of gravitational collapse. So essentially, the collapse gets accelerated, and then the two collapse, and then you're going to see three things. You're going to see the emission of gravitational waves. You're going to see a jet that we call a short gamma ray burst that happened about 2 seconds later. And then you're going to see the remnant, which is the light being emitted, but what it's believed to be heavy nuclei produced in this event. So we know very well where all the nuclei are produced, all the way to iron. Beyond iron, it has always been an open question. And now we have the first evidence in favor that maybe neutron star mergers are the site for the production of the heavy elements in the cosmos. So let's say, here we go. So you see, you have two neutron stars. When they're very far apart, you cannot tell whether they're black holes or they're neutron stars. Then they start emitting and deforming each other. As they deform each other, they get mass quadruples, and they emit a tremendous amount of gravitational waves. You saw the jet 2 seconds later, that was the short gamma ray burst. And then the little thing that remains is not a supernova, but it's a kilonova. But the interesting fact is that it gave some insight into the production of the heavy elements in the cosmos. There is also this very nice cartoon. And then you will see that essentially what happens here, LIGO is detecting the gravitational signal. And then you're going to hear the chirp, which I guess, and then you're going to hear the bell 2 seconds later. So the first event is the emission of gravitational waves. 2 seconds later, the Fermi Gamma Ray Telescope gets the short gamma ray burst. And then essentially 70 observatories all around the world operating at all different wavelengths essentially look at the remnant, which is called the kilo. So why are these very, very interesting? So what happens and how can they inform the mass radius relation? So let me stop, forget about gravity for a second, and let me tell you something that you've seen many, many, many times, which has to do with electrodynamics. And it's the phenomenon of the electric polarizability of a medium. So imagine that you have, let's say, a drop of water, and then you have parallel plate capacitors, and then you put the drop of water in there. So basically what's going to happen is that you have an external stimuli, the electric field, and the medium is going to respond by creating a polarization. Positive charge is going to separate from negative charge. And then there is a unique characteristic of the medium that it's encoded in this susceptibility. So basically, if the electric field is not very strong, then the response of the medium is linear, and then the polarization is related to the electric field via a characteristic of that medium, which is the electric susceptibility of the medium. So now, what is the tidal deformability doing? So the tidal deformability is essentially the same effect, but with gravity. Of course, there are no mass dipoles. So the lowest order one is a mass quadrupole. And essentially what happened is, imagine that you have one of the neutron stars, and the neutron star induces a tidal field that polarizes the companion star. So that companion star, in response to that tidal field, generates a quadrupole, a mass quadrupole. And in the same way that there is a linear response which characterizes the object, there is a linear response that creates a quadrupole, which is encoded in this quantity, which is called the tidal deformability or the tidal polarizability. And the most remarkable thing is that GW170817 already told us what is the tidal deformability should be, with some limits. And basically what it's telling you is, so this is from the discovery paper. This is really from the paper that produced the results, that confirmed the results, and said that this event is actually favoring more compact stars. That means that if you have, for a given mass, then tidal deformability like small stars, compact stars. And that, of course, provides an enormous amount of information for the equation of state. So here in a cartoonish way, I like to say that the tidal deformability measures the fluffiness or the stiffness of a neutron star against deformation, and it's very sensitive to the stellar radius. If you do a calculation, you can prove that the tidal deformability is very strongly dependent on the ratio of the radius of the star to the mass of the star raised to the 5th power. So you have a very strong lever arm, and then there is a prefactor here that is called the log number, which you have to calculate, and honestly, that's the hardest part of the whole calculation. But in here, it already encodes the importance. The importance is because if you measure the tidal deformability, you can constrain the compactness of the star, or namely the ratio of the radius of the star to the mass of the star. Okay, so that's GW170817, and then 2019 comes, so of course GW17 is 2017. 2 years later, we get the report of the most massive neutron star ever measured. And this is done by something that is the generalization of Kepler's law. It's not the generalization, but it's Kepler's law plus corrections from general relativity. So basically what happens is that if you remember from your classical mechanics class, there is, of course, Kepler's third law, which is telling you that the ratio of the cube of the semi-major axis to the square of the period is essentially, as far as planets is concerned, a universal quantity. Because planets are so light relative to the sun, that's the way you can calculate the mass of the sun. Of course, that doesn't mean that it's only true for masses, for planets and the sun. It's also true for any binary object. But the problem is that you have a degeneracy. That Kepler's law is telling that the only thing that you can measure, for example, in the case of in which the binary is a neutron star and a white dwarf, is the mass of the two. But I just want the mass of the neutron star. So how do I break the degeneracy? Well, there is this quantity and this effect called Shapiro delay, often called the fourth test of general relativity. And the idea is relatively simple, even though, of course, the calculation is not. And the idea is that if you have, for example, the white dwarf star in here, and then you have emission from the neutron star in here, and we are sitting here, so your eye is over here, then if you are in this configuration, then the radiation that's going to be emitted by the neutron star is going to dip into the gravitational wave of the white dwarf star, and it's going to be delayed when it gets to the observer. If, on the other hand, you exchange the position of the white dwarf at the neutron star, then the emission from the neutron star is not delayed. So this is called pulsar timing, and basically this is what you see in the different configurations. And you see that there is a time delay of about 10 microseconds, but the formula essentially completely isolates the mass of the white dwarf, and it's independent of the mass of the neutron star, because the radiation is dipping into the gravitational wave of the white dwarf. So then, basically, by looking for long periods of time, that's the idea of pulsar timing, then you will get extraordinarily good statistics. And of course, if you can measure the mass of the white dwarf, you can extract the mass of the neutron star. In 2020, we got the report of the most massive neutron star to date, which is essentially 2.1 solar masses. So that tells you also immediately that if you build an equation of state and you calculate the maximum mass that you can have before the star becomes a black hole, if it's below 2.1, then your equation of state has to be refined. So we have tidal deformability, and then we have maximum masses as the constraint. So now let me go to the newest toy in town, which is NICER, which stands for the Neutron Star Interior Composition Explorer. So NICER was launched from Kennedy Space Center aboard a SpaceX Falcon 9 rocket. And if you remember, that's the company owned by Elon Musk. So Elon Musk provided the rocket, and then 2 days later, essentially, it docked at the International Space Station. So if you go to the International Space Station, you will see the NICER instrument. And what NICER does is to measure the compactness of the neutron star, and it sounds like magic, by looking at the back of the star. So NICER can look at the back of the star because, of course, we know from general relativity that light will be bent. So if you have a very compact object, so let's suppose that you have a neutron star here. So you will be able to see the light coming from the back of the star. The more relativistic or the more compact the star, namely the smallest radius to a given mass, the more that the light is going to bend, and that's what NICER is going to try to infer, and then give you some information about the compactness of the star, which again involves the mass and the radius. And the way they do it is they look at sources of neutron stars that have these hotspots. These hotspots are produced by charged particles, which leave the star because of the enormous magnetic field, but because of all the twists in the magnetic field and the complicated magnetic fields that I have to confess I do not understand, they crash back to the star, hit the star, and produce these hotspots. So basically what NICER is looking is at the hotspots. So you have a picture here of the hotspots, and then basically you see what happens if the star is much compact or less compact. So essentially that's what NICER has been doing, and it has been doing it for 2 stars. Let me just play this thing with it, right? So the idea is that even when this hotspot is behind the star, you can still see the light, and then you see that no matter what the star is, if the star is compact, then it never goes to 0, the flux that you receive. And the more compact the star, the more that these minima are filled in. So that's a way for them to extract the compactness of the star. The more compact, the more light bending that it will happen. And then we had 2 measurements from NICER, but the one that I want to point out is, remember I just told you about the most massive neutron stars that we have discovered. They have actually measured the radius of the star. So we have the simultaneous mass radius determination of a neutron star. They have done a measurement before for another object that had a mass of about 1.4 solar masses. And believe it or not, even though neutron stars is a field that is very, very old and mature, so in 1967, Jocelyn Bell discovered the first pulsar. These 2 are the first determinations, simultaneous determinations of the mass and the radius of neutron stars. Okay, so now let's go. We already said what happens in GW170817 in the cosmos. Let's see what happens here on Earth. So there is, remember that I talked about this quantity L, which effectively it's telling you what is the pressure of pure neutron. Yes?
Yeah, how do you separate the mass from the radius? Since you're the Greek letter, whatever it is.
Yeah, it's the same C. Yeah, my students say that. So the way you separate it is because pulsar timing gave you the mass of that very heavy pulsar. So you measure C.
Is it a binary orbit?
So which one?
So will the neutrons are?
No, not these ones were not.
So how do you separate?
Okay, so let me just go back if I may. So the question is, how do I separate M from R if this is all that you measure, right? Well, imagine that NICER measures M over R via the hotspots, right? Electromagnetic information here. And then you go back and you say, can you use Shapiro delay to know about the mass?
So it's in a binary.
So these, yeah, so these,
Okay.
Okay, okay. So this, yeah, so this is the binary that we knew its mass, and now we know its radius. Okay, so then what happens here on Earth? So at the very beginning, I was alluding to this quantity L, which is essentially the pressure of pure neutron matter. And the question is, how do I determine a quantity which is not a physical observable, but it has an enormous impact on the physics of the neutron star? So basically, what we came up is with a correlation between 2 quantities, this quantity that we're after, and this quantity that we call the neutron scheme of LIGO-208. And let me explain what is the neutron scheme. So in a system like LIGO-208, you have 126 protons and you have 82 neutrons. Right? 82 protons and 126 neutrons. So you have an excess 44 neutrons. And the question is, where are those neutrons going to go? So basically, you form like a system with 82 protons and neutrons. Let's say that's the uniform system. And then you form a scheme around that core. And the difference between the radius of the neutron distribution relative to that of the protons, we call it the neutron scheme. So the neutron scheme is essentially this thing that sticks out. So imagine this is the distribution of protons. This is the distribution of neutrons. And then the neutron scheme is going to tell you how much the neutrons extend beyond the proton. And then you go and you ask many of your friends that can do calculations both for infinite matter and for finite nuclei. And you say, can you plot your predictions along this line? And it turns out that with a fidelity of about 0.98, with a correlation coefficient of 0.98, you can see that this scheme is acting as a proxy for the quantity that you're trying to extract, the pressure of pure neutron matter. So basically, you do an experiment in the laboratory, which is going to provide you with a quantity in femtometers, 10 to the minus 15 meters, that correlates very strongly with it. It's the same L that I mentioned here that actually correlates very strongly with the radius of a neutron star. So the beauty of this project is you make an experiment here, you extrapolate to 80 orders of magnitude, and you see essentially the same correlation. So this quantity L, this pressure of pure neutron matter in the vicinity of nuclear saturation, is going to determine the extent of the neutrons in a nucleus like lead, but also the size of a neutron star, which again differ by 18 orders of magnitude. So the question is, how are you going to do the experiment? And the experiment has just been completed a couple of years ago. And I'm going to explain it in the next slide in a little bit more detail. So basically what you do is you do what's called parity violating electron scattering from a nucleus. So imagine that this is lead-208. And then normally what you have is if you have an electron, which scatter elastically from this nucleus, you emit, most of the time you emit a photon. The photon couples to charge, namely the protons, and this is an exquisite way of determining the distribution of protons in a nucleus. And this has been done for many, many, many decades. However, you can also get information about the neutron distribution, because once in a while, the electron not only interacts via the electromagnetic force, but also via the weak force. So the Z0 boson is the carrier of, or at least one of the three carriers of the weak force, and then it emits a Z0, and the question is, how does the Z0 couples to the nucleus? So there is a very interesting relation or dichotomy between the coupling of a photon and a Z0. So if you ask in terms of quarks, how does the photon couple to quarks? Then you say, well, an up quark has charge 2/3, that's the way it couples, down quark minus 1/3. You add two of these, one of these, you get that the charge of the proton is 1. You add two of these, one of these, the electromagnetic charge of the neutron is 0. Now, if you look at your table of the standard model weak couplings, you find that the up quark now has essentially 1/3, down quark minus 2/3. So now the 0 goes to the proton and the minus 1 goes to the neutron. So Z0s couple very, very strongly to neutrons. And if you do this experiment, which is essentially an interference experiment, which measures the parity violating asymmetry, you get information about the only thing that you do not know here is this quantity here. We call it the weak form factor of the nucleus. You extract these, and then that gives you information about the neutron scheme. This is the lead radius experiment. And then very recently, it came with a value of 0.283 plus or minus this value. And the important thing is that suggests that L is large, namely that this scheme that we form, it's pushing very hard against the neutrons, making a big scheme. And if L is large, that means that we also expect the radius of the neutron stars to be large. So that's the correlation that I mentioned. So let me just try to summarize this in a way that I like very much. So you know about in cosmology, one of the hardest quantities to measure is the distance to the object. So cosmologists have come with this cosmic distance ladder, in which essentially you use different methods to try to establish the distance to the object. So ones that we learn in our astronomy class is parallax, but then you just go up, and then you get it even more sophisticated ways. And for example, we know about the standard candle that thermonuclear or thermonuclear or type 1 supernova are used to infer distances. I think the same thing we can do here with the equation of state. We have different ways of determining the equation of state at different densities. I mentioned the experiment that we do here on Earth, trying to calculate parity violating electron scattering to tell you how the density between 0.5 and 1.4, let's say, nuclear matter saturation density. You can do heavy ion collisions here on Earth, which sample a little bit high density. NICER has a broader range, and then you have gravitational wave observatories, and finally you have the pulsar timing that determines the maximum mass. So this is meant to illustrate that really it's a very diverse interdisciplinary field, but because of the different techniques, then you need them all to be able to constrain the equation of states at different densities. Okay, so that's basically the idea. Now let me put together some of the things. So here is just some of the constraints that I have put in here, but I think a little bit more illustrative might be, this is the plot that I show for the mass radius relation in 2010, right? And remember that I told you that in 2010, we only had one measurement of the maximum mass, no measurements of radius. So now if you put these things in here, so these purple things have been some theoretical analysis that came after LIGO, after the gravitational wave observatory provided us with constraints on the tidal deformability. We used to have one star here, now we have 3 stars in here. For this star, the most massive one, now we have a radius from NICER. And for the other one, which was around 1.4, we also have a radius from NICER. So now things are getting much more interesting because we're getting really information both from the lab and from astrophysics to constrain the equation of state. And 2 things that are very interesting are the following. One is obvious, that if you have an equation of state, you can produce a mass radius equation. The other one that is not very well known is the opposite. If you have a lot of mass radius relation points, you can invert the equation and you can invert the mass radius relation and provide an equation of state. So I think we're getting close to this point, and then an analysis that we are trying to do in response to this data is to get a much better constrained equation of state coming from this information. So we have seen some tension, and let me describe that for you in here, right? So by laboratory experiments, I'm telling you about the neutron skin thickness of lead. They suggest a very large value of L, a very large value of the pressure for pure neutron matter, a stiff equation of state. So this is suggesting that we have a stiff equation of state at the density that you can probe in the laboratory. The gravitational waves suggest small stellar radii, and that is a region that you can probe twice nuclear matter saturation density. And then pulsar timing tells you that eventually your equation of state will have to stiffen again because you have massive neutron stars, and without the pressure that pushes hard, you will never be able to account for that. So we have stiff, soft, and stiff. And the idea is that maybe what nature is trying to tell us is that there might be a phase transition in this intermediate region in which the equation of state softens, but then eventually stiffens. And that's an interesting possibility. A possibility that got even more dramatic because the initial number that was produced by the LIGO collaboration, which was comfortable within these models, has been now revised to a very small number. And then this number over here, which is very small, is very, very hard to reproduce. So we're seeing tension, and tension is always good in physics because it teaches some interesting results. Okay, so let me finish with something that is dear to Vince and my heart. And for the young people in the audience, let me tell you about this quote. So who ordered that is a quote attributed to Isidoro Rabi. The first time that he heard that there is a new particle that for all intents and purposes is identical to the electron, but it's 200 times more heavy. And his comment was, who ordered that? So in the context of our work, So I told you about the P-Rex experiment, which is trying to understand how big is this neutron skin in lead. This experiment was followed by C-Rex. So instead of the P, now we have a C. So the experiment was done in calcium-48. So as theorists, one of the things that we like to do is we say, well, if the correlation between lead-208 and calcium-48 or other nuclei is very strong, then basically I can use P-Rex to predict what the neutron skin of this nuclei is going to be. The blue one, in particular, is the case of calcium-48. So in calcium-48, I say that consistent with P-Rex, I expect that the neutron skin in lead in calcium-48 should be at least 0.21 Fermis. So in the last Division of Nuclear Physics meeting, the collaboration reported that instead of being 0.2, is essentially 0.1. So my first reaction is to order that. That is completely against our notion that these two quantities are going to be very correlated. So if one is large, the other one has to be large. So this is something that the experimentally showing in their plot, they also showed this. So this is a little bit different way of telling about the neutron skin. So the experiment, the C-Rex experiment on calcium-48 likes this thing. You can see here the abbreviation DOM. So Vim and collaborators like this thing. You can see that I also like big things. So the question is, how do we resolve that? And we have at this point no idea. So I can confidently say that in my opinion, there is no theoretical framework within the nuclear physics community that can simultaneously reproduce a very thick skin in lead and a very thin skin in calcium-48. So on that note, I'm just going to tell you that working in this field is incredibly fantastic because it's a collection of all different disciplines. You try to become expert in some. My field is nuclear physics, so I'm very, very happy to work on the equation of state. But as I can already tell you, all possible implications from other fields. Most of this work has been done, of course, always by very talented grad students. I have an older generation, an old generation, a new generation, and with that, I'm going to thank you for listening.
Thank you very much. It's a nice talk. So do we have questions or comments? Yes.
So in this mass radius relationship, there should be like a parameter for the spin of the star. Does that widen that?
So the spin, I don't remember how accurate they measure the spin, but the extraction of the tidal deformability puts into account the analysis puts everything into account, and then the only thing that I, as a nuclear physicist, see is the extraction of the tidal polarizability, which is encoded in some high-order post-Newtonian parameter in the gravitational wave feature. So I don't know the role of the spin of the particles.
The connection between finite nuclei and infinite matter is gone through a model that I would refer to as a mean field approximation. And it also involves a limit because of that. And so how sure are we really that we can make this connection?
Yeah, so oops. No,
I was calm.
So let me see. So this connection, and actually I had a very, very useful conversation this morning with Mark and his team, and the question was exactly the same, right? If you are putting all these mean field, how robust is the correlation? Personally, I think that the correlation will go beyond mean fields. I can explain in detail. Basically, what happens is that the size of the skin is a competition between surface tension, which wants to have everyone parting in a small place, and the symmetry energy, the density dependent of the symmetry energy, which wants to move all the neutrons to the exterior. So from that point of view, I think it's a robust physical argument, which is validated by mean field models. But I have to completely agree. This is a very particular set of models, and then the correlation has to be tested further.
Yeah. I mean, one of the problems I have with connecting a finite system with an infinite system is not necessarily so much for only neutrons, but for symmetric. Where, the argument is too detailed, but to make the link between, let's say, an empirical mass formula and the saturation energy of nuclear matter is a very optimistic state.
Yeah, but I mean, I don't know how much detail we should go.
No, no. It's fine.
Lee?
So let's say that the small skin of calcium and the large skin of lead were correct. Is there another observable, an isovector, a dipole that can be used to say that, for example, that is inconsistent with that other observable in this other sector? Is there something else?
So
Now that we have really divergent.
yeah. So if this holds, I scratch my head, right? And I've been scratching my head since they announced it. So there is another observable, which is clean. And by clean, I mean that it only requires electromagnetic presence, which is precisely what you say, the electric type of polarizability, which essentially is related to a photoabsorption cross-section.
Right.
Even though it's still a completely electromagnetic experiment, I think the extraction of the electric type of polarizability is still a little bit model dependent. But so far what we've seen is the following. So the values that we have obtained from experiment for the electric type of polarizability.
Is this for like 10, 112 and 124?
It's 214, 112. I don't know if there is 124 measurement for that. But there is for lead, for example, and there is for calcium 48. And then a very thick skin, like suggested by lead, is inconsistent with those measurements of the electric type.
Again, through the mean field.
Through the mean field.
Wait a moment. I want to make sure I heard that right. So you said that the polarizability for alpha for lead was inconsistent with the large skin for lead. Is there an alpha for 48?
Yes, all of them are inconsistent. So
wait a minute.
So
inconsistent in which way?
In which, if you assume the constraints from P-Rex 2 and say, what should I obtain from a theoretical perspective? What should I predict for this quantity, for these nuclei? They are inconsistent with what is measured in the laboratory at the mean field.
So it's inconsistent with P-Rex and C-Rex?
Well, C-Rex, I haven't done anything with C-Rex because the paper has not been published, but it's inconsistent with P-Rex at the mean field level. I had a very, very nice referee, and that's the conclusion that we reached.
Okay, so we were both on a proposal, on different ends of a proposal at the Free Electron Laser Lab at Duke for measuring alpha for 112 and 124.
Right.
Okay. And those data were taken, and they're somewhere in the depths of Livermore. I don't know what's happening. Okay. Because I haven't heard about it. Somewhere in the middle of COVID, they went dark. And would that help resolve it, or?
Well, I did calculate. See, I did calculate for tin. So this behavior is very universal in the sense that the alpha Ds that have been measured seem to suggest a soft symmetry energy. P-Rex seems to suggest a stiff symmetry energy. And in that sense, these two pieces of data are inconsistent.
Well, but if you threw away P-Rex, then you'd say the world was fine.
I'm not going to take away throw away P-Rex. I mean, imagine that you
I
were.
didn't spend any time on it, so I have no problem throwing it.
No, I mean, in my personal opinion, these are very clean experiments. People have worked.
So C-Rex.
Yeah, so it's C-Rex. So
But it's not yet
They are
published.
published.
yeah, but then still, right? Even if C-Rex is
Talking
bad,
about it. for
that's
half
not
a
their problem, right? They are providing nature. It's our problem, right? How we reconcile all these seemingly discrepant. I vouch for the experiment, which is not something that I do often.
because we weren't involved.
Okay, more comments or questions? People online?
Yeah.
Maybe their own food.
Okay, if I think there are no more questions or comments, thank you, Jorge. We are done.